Hey everyone, next in our series is going to be a look at section 3.4 in our concepts review. Remember, these are all AP Calculus review problems, so let's get started. Okay, so these problems are a series of problems that will help us try to concrete the relationship between the derivative of a function and the function itself. Most of these will be related to you as position and velocity. So it is up to you to remember that velocity is the derivative of position. So when we look at this very first one, the graph shows the position st of a particle along the horizontal axis. We should know that we're not looking at the derivative of a function. We're just looking at the function itself. Okay, here's a nice piecewise curve. And it says, now when is the particle moving to the left? So let's take a look at each one of these distinct regions on the line graph, and let's figure out, is the function moving to the left or to the right? So we're going to start off with this first piece right here, from t equals 0 to t equals 1. And as you can see, we start off with the position at -4, and then the position is at -2. So imagine position's -4, position's at -2. It looks as though we are moving to the right on that one segment from t equals 0 to t equals 1. So although that's not an answer for question A, that is a answer for question B. So from 0 to 1, let's put it here, from 0 to 1, we're moving to the right. A couple things you should also know about that one. The slope is positive. Well, are there any other places where the slope is positive? Indeed, there is. From over here to about here. So in that stretch of graph from t equals 3 to t equals 4, again, the position at t equals 3 is -2. The position at t equals 4 is +2. So you can imagine that that particle is moving to the right again. So we'll put another section of the graph. This is from t equals 3 to t equals 4. Okay. Now let's take a look at those horizontal pieces. I think you see them already. From t equals 1 to t equals 3, well, what's happening? The position at the beginning of that blue section that I've highlighted, the position is -2. And then at the end of that section, the position is still -2. So from t equals 1 to t equals 3, the particle is not moving at all. So that is where one section where the particle is standing still. So from t equals 1 to t equals 3. Well, are there any other horizontal places here on the position graph? Certainly. From here to here, from t equals 4 to t equals 5. So that goes along with letter C, from 4 to 5. All right. Take a deep breath, and let's move on to the last section, which I didn't highlight, which is the part with a negative slope, from t equals 5 to t equals 7. So look at what we're saying here. When t equals 5, the position is 2. When t equals 7, the position is, I believe that's -2. So we're starting at 2, and then we're going backwards to -2. So for that section, our particle is moving to the left. And I believe that is the only place where we have a negative slope. So from t equals 5 to t equals 7. Remember, it's just my preference to write these in set notation. If you want to write these with inequality signs, feel free. Okay, so the next part here is we're going to graph the velocity of the previous function. So let's see. From 0 to 1, I think we have a slope of, we have a slope of positive 2. And you can really quickly do that here. The slope is the difference in the x-coordinates, 1 minus 0, over the difference in the y-coordinates, negative 2 minus negative 4. No, I did those backwards. Let me do a real quick fix here. So we got 1 over 2, so the slope is equal to 2. So you can see the slope is 2. We're moving to the right, so that jibes with what we knew there. So from t equals 0 to t equals 1, we should have a slope of 2. And it is a slope of 2 everywhere. Does that slope change? No, it does not. At least it doesn't change between t equals 0 and t equals 1. Moving on. What about from t equals 1 to t equals 3? Well, the slope of that curve is clearly 0. So we can just go ahead from t equals 1 to t equals 3. We'll say the slope here is 0. There we go. Slope of 0. Our next section is from t equals 3 to t equals 2. Maybe we should figure out that from t equals 3 to t equals 4. Let's figure out the slope here. And let's not make the same mistake I did last time. From t equals 3 to t equals 4. The y-coordinate when t equals 4 is 2. The y-coordinate when t equals 3 is negative 2. So this looks like a slope of 4. Okay, so from 3 to 4, we've got a slope of 4. Okay. And then not the last piece. From 4 to 5, again, we have a horizontal line for position. So the slope of a horizontal line is 0. So let's put a 0 there. And then that last piece, from 5 to 7, what is a slope? Well, the y-coordinate at 7 is negative 2. The y-coordinate at 5 is positive 2. 7 and 5, so that is negative 4 over 2, which is negative 2. So from 5 to 7, we've got ourselves a slope of negative 2. All right, there we go. Looking good. Next, speed. Oh my gosh, speed. Well, speed, if you'll remember from your physics class, that's just the absolute value of velocity. So this graph is going to look just like the previous graph, except in one notable place. And I already messed that up. 0 to 1. 1 to 3. The slope is 0. The absolute value of 0 is 0. From 3 to 4, the slope is 2, and the absolute value of 2 is 2. From 4 to 5, the slope is 0. I should be saying the velocity is 0. So the absolute value of 0 is 0. And then here's that one change. From 5 to 7, the velocity is negative 2, and the absolute value of negative 2 is 2. So the absolute value curve is just like the velocity curve. It's just that everything is above the axis where it would have been below the axis. So there's our speed graph. When is the particle moving the fastest? So fastest means greatest speed. So where is the speed greatest? I think that is this little chunk of graph right there. So that is when t goes from 3 to 4. Okay. From 3 to 4, we've got the greatest speed. Next. This graph is the velocity curve, so already we're different than in question 1 because now we're looking at velocity. We are not looking at acceleration or position. So when does this particle reverse direction? Right? So let's think about what's happening here. From t equals 0 to t equals 1, our particle is moving to the right. How do I know that? Well, from 0 to 1, the velocity is positive, and as we know, positive velocity means that we're moving to the right. Okay? Over here, from t equals, I believe that's 3 to t equals 6, again, the velocity is positive because the velocity graph is above the axis. Remember, we're looking at the velocity graph, not the position graph. Which means that for this whole chunk right here, from t equals 1 to t equals 4, the velocity is negative because the velocity graph is below the axis. Therefore, the velocity is, or the particle is moving to the left. When does this particle reverse directions? Well, that happens in two places. It happens at t equals 1 and t equals 4. So this is a big thing here. Once you're reading the velocity graph, you have to know what does it mean when the velocity curve crosses that x-axis. Okay? And that means a change in direction. Now in the AP test, you're pretty much always going to be given a velocity curve. It's very rare for you to actually get a position curve. So you have to get really good at reading these velocity curves. So where do we have constant speed? Well, speed is the same thing as the absolute value of velocity. Is there any stretch of t of this graph where the velocity is remaining constant? Okay, and I think we have it from t equals 5 to t equals 6. So let's write that here. The particle is moving at a constant speed for the interval t between 5 and 6. When is this moving at its greatest speed? So when is the absolute value of velocity the greatest? And so the real quick way to figure this out is visually, when is the graph, the curve, as far away from the x-axis as possible? So you got a couple of candidates here. Right over here, the speed is 2. Here also, speed is 2. And then the other place where we are as far away as possible from the axis is right here. And here, since the velocity is -3, the speed is 3. So when is it moving at its greatest speed? That's going to be at t equals 3. Okay? Letter D. We're now being asked to graph the acceleration where defined. So I'm going to need both of these graphs on the same page here. Now this is very similar to what we were saying when we were translating the position graph to velocity. Now we're transitioning from the velocity graph to acceleration. So we're just looking at the slopes at all the different places. So I think from t equals 0 to t equals 2, we've got the same slope. So this slope here, let's see, the velocity here at t equals 2 is -2. The velocity at t equals 0 is 2. And then what do we say, from 2 to 0? 0 to 2, I should say. So that looks like -4 divided by 2 is -2. Right, so from 0, t equals 0 to t equals 2, we have acceleration of -2. Okay, next one, from t equals 2 to t equals 3. It looks like the slope of my velocity curve changed a bit. Let's see, the position here, or the velocity at t equals 3 is negative 3. The velocity when t equals 2 is negative 2. And then we have 3 minus 2. So how much is this? Negative 3 minus negative 2 is negative 3 plus 2, which is negative 1. So we have a acceleration of negative 1 from t equals 2 to t equals 3. Remember, the acceleration is equal to the derivative of velocity. So it's equal to slope. Okay, the next section here that has the same slope would be from t equals 3 to t equals 5. That's where the slope of the velocity graph looks the same. So from 3 to 5, the slope is equal to, let's see, when t equals 5, the velocity is 2. When t equals 3, the velocity is negative 3. And then we said 5 to 3. Yes, we did. See, 2 minus negative 3, 5. 5 minus 3 is 2. So that's a positive 2.5. From t equals 3 to t equals 5. And then from 5 to 6, I think you can see the velocity graph is horizontal, which means it has a slope of 0. Okay. A particle moves, this is a new question, number 3. A particle moves along a vertical coordinate axis so that its position at time greater than or equal to 0 is given by the function, and then it looks like a cubic function, where s is measured in centimeters and t is measured in seconds. We'll probably need those units sooner than later. Find the displacement in the first 6 seconds. So displacement, yeah, I'm spelling that right, is, well, it's just the change in position. So let's take a look at what graphs we have. Very important. Well, we don't have graphs. We have an equation for position. So all we need to do to find the displacement in the first 6 seconds, that's just going to be equal to the position when t equals 6 minus the position when t equals 0. So let's quickly plug that into the calculator and figure that out. Here's our calculator. You'll notice that I went ahead and I put the position function already into y1. So all I need to do now is go to the home screen and take a difference, y1 at 6 minus y1 at 0, and that should get this answer to me, 108. We're measuring in centimeters, so we better put a centimeters here, 108 centimeters. Moving on to question B. Find the average velocity over the first 6 seconds. So I always like to tell my students the average of anything in velocity. I don't care what they tell you in algebra. I don't care what they told you in physics or whatever. Velocity in calculus is always, or average in calculus is always, 1 over b minus a, integral from a to b of f of x dx. Every average in AP Calculus will be done this way. So we're trying to find average velocity, so we need to put the velocity into this equation. Over the first 6 seconds, so I don't think you'll mind if I just go from 0 to 6 of velocity t dt. Well, how do I do this? They didn't give me a velocity equation, right? That's what you're thinking? Well, they did give you the knowledge of the position. The derivative of position is velocity. So if you integrate velocity, you get position. Let's write that over here. The integral from a to b of velocity of t dt, that's equal to the position at b minus the position at a. And that's all you need to solve this. This is equal to 1/6 the antiderivative of velocity, which is the position at 6, minus the position at 0. Luckily for us, we have already calculated the position of 6 minus the position at 0. It's 108. So what is 1/6 of 108? It's 18. So let's write that here, 18. What units should we use? Well, it's going to be the same units as velocity. Velocity is in centimeters per second. Find expressions for velocity and acceleration. Okay, now they're asking me to find derivatives. So the expression for velocity is the derivative of position, which is 1/2 t squared plus 4t. And then the acceleration is just the derivative of velocity. So the derivative of velocity is what? T plus 4? Yeah, that looks right. And for what values of t is the particle moving downward? So just like the previous one we were doing, particle moves downward if the velocity is negative. Just like if we have horizontal motion, particle moves to the left if velocity is negative. So when is velocity negative? When is 1/2 t squared plus 4t, when is that less than 0? Okay, I think we could do some solving here. First of all, we can factor. Actually, before we factor, let's multiply everything by 2. That'll make this solving a little bit easier. So t squared plus 8t is less than 0. Now we'll do some factoring. T and t plus 8 is less than 0. So this particle has the potential to turn around at t equals 0 and t equals -8. Well, we don't have to worry about -8 because, because t is greater than or equal to 0. So what this is telling me is that for t greater than or equal to 0, this function is always, or this particle is always moving in the same direction. It's never turning around. It can only turn around if the velocity is 0. So what is the velocity at any point from 0 to positive infinity? Well, let's just figure one out. What's the velocity when t equals 1? Well, that's going to be 1/2 of 1 squared plus 4 times 1. I don't care what the answer is. I just know that that's greater than 0. So this says to me, if the particle never turns around and the particle is observed to be moving in a positive direction or upwards, that means that the particle is never moving downwards. So for what values of t is a particle moving downwards? Yeah, never. Okay. Folks, this is a long one, so what we're going to do is we're going to cut this off here because we've already been talking to you for 25 minutes, and we're going to do the second half in the next video. So meet me at the next video. I'll see you later for the second half of our 3.4 key concepts review.